Find the truth function defined by the propositional formula, left parenthesis, P0 and not P1, right parenthesis, implies P2. This is essentially the problem of finding the truth table of left parenthesis, P0 and not P1, right parenthesis, implies P2. The truth function is a function of three variables, as there are three proposition symbols in the formula. Let us denote the value of P0 by x0, the value of P1 by x1, and the value of P2 by x2. So we need a function, f of x0, x1, x2, of the three variables, x0, x1, and x2, so that if x0 equals v of P0, x1 equals v of P1, and x2 equals v of P2, then f of x0, x1, x2 equals v of left parenthesis, P0 and not P1, right parenthesis, implies P2. We build the table of f step by step. To find the value of f of 1, 1, 1, we compute what the truth value of left parenthesis P0 and not P1 right parenthesis implies P2 is when P0, P1, P2 are all true. It is clearly 1. We now make an observation. Left parenthesis P0 and not P1 implies P2 is true when P2 is true. So we can immediately fill three more values to the table of f. The next observation is that left parenthesis P0 and not P1 right parenthesis implies P2 is true also if P0 is false, because then P0 and not P1 is false, and hence the implication true. There are just two values left to compute. In the first case, we need a value for f of 1, 1, 0. The value is 1. And finally, f of 1, 0, 0 is 0. The table is ready. In each case below, find a propositional formula using not, and or, which defines the given truth function. The first truth function. It is a column of ones. This truth function is a constant function, constant 1. So if we take the formula P0 or not P0, it is a perfect answer. This formula is a tautology, so its truth value is always 1. It does not matter that P1 does not occur in the formula. But there is no problem adding it to the formula either, and we get the formula left parenthesis P0 or not P0, right parenthesis, and left parenthesis P1 or not P1, right parenthesis. But this is superfluous. The second truth function. This is a non-constant function, and we apply the method of disjunctive normal forms to it. There are two 1 rows, the second and the third, so we build a disjunction of two formulas. The first disjunct is P0 and not P1, and the second disjunct is P0 and not P1. So the formula is left parenthesis P0 and not P1, right parenthesis, or left parenthesis not P0 and P1, right parenthesis. Now one can easily check that, indeed, this formula defines the given truth function f. This can be seen by simply going through the possible arguments x0, x1, and checking in each of the four cases that the two functions, the given function f, and the truth function defined by our formula, give the same answer. The third truth function. This is again a constant function. There are no 1 rows, so we could not use the disjunctive normal form method even if we wanted. Instead, we use common sense. Any contradiction is false under any valuation. So we take, for example, p0 and not p0. This formula defines a truth function which is constant 0. The final truth function. Again, we have two one rows. We have to build a formula using only not, and or, so we cannot take the formula p0 if and only if p1, although this formula clearly defines the given truth function. So we use the method of disjunctive normal forms. There are two one rows, the first and the fourth, so we build a disjunction of two formulas. The first disjunct is p0 and p1, and the second disjunct is not p0 and not p1. So the formula is left parenthesis p0 and p1, right parenthesis, or left parenthesis not p0 and not p1, right parenthesis. Now it remains to check that indeed this formula defines the given truth function. As above, this can be seen by simply going through the possible arguments x0, x1, and checking in each of the four cases that the two functions, the given function f and the truth function defined by our formula, give the same answer. Find a propositional formula using not, and or, which defines the truth function. This problem clearly calls for an application of the disjunctive normal form method. Let us see how it works. There are 6 one rows and 2 0 rows. It is too bad that the disjunctive normal form method focuses on the one rows, and there are so many of them. Let us use a trick. By focusing on the 0 rows, we can build a formula whose negation is the requested formula. So we start our defining formula with a negation, and then write a formula which has a truth value 1 on exactly the 0 rows. There are 2 0 rows, so we build, inside the negation, a disjunction of two formulas. The first is p0 and p1 and p2, and the second is not p0 and p1 and p2. The final formula is not, left parenthesis, p0 and p1 and p2, right parenthesis, or left parenthesis, not p0 and p1 and p2, right parenthesis, right parenthesis. This formula works, but at the same time it looks suspiciously independent of the truth value of p0. So let us try a simpler formula, not, left parenthesis, p1 and p2, right parenthesis. We need to check that the truth function defined by not, left parenthesis, p1 and p2, right parenthesis, is the function f. This is easy to do. We note that f of x0, x1, x2 is independent of x0, just as the truth function defined by our formula is. For the four possible values of x1, x2, we note f and the truth function defined by our formula give the same value, so we are done. Show that the ternary truth function is universal. Note that f of x, x, x equals 1 minus x, and f of x, x, z equals 1 minus xz. Thus, f of x, x, z, f of x, x, z, f of x, x, z equals xz. This shows that we can express negation and conjunction in terms of f. But we already know that the set negation conjunction is a universal set of connectives, so we are done. Show that the set conjunction disjunction of connectives is not universal. It is easy to see that any connective f of x1 down to xn, defined in terms of conjunction and disjunction, satisfies f of 1 1 equals 1. How? This property holds for conjunction and disjunction, and the property is preserved by composition of functions. Therefore, it holds for every connective defined in terms of conjunction and disjunction. Thus, it follows that negation cannot be defined in terms of conjunction and disjunction.